Hello everyone, welcome back. This is, I guess, week 3 of updates. Today is not going to be that much, and that's largely because I'm working on a lot of concurrent things at the same time, and while a lot of them are in a very good state, they're not quite enough for me to show off. However, we're going to kind of start with an introduction to our launch vehicle. As you can see, I've got a lot of Wikipedia tabs open today. So let's go take a look. So, obviously one of the goals with the design and feasibility of these probes, these Martian landing probes, is we need to get them there. And, we need a launch vehicle. They won't just appear. And of course, this mission is also extremely flexible, where the probes themselves are designed to be self-contained, and so they can do their own retrograde entry burn, or EI burn, and so they could be a rideshare mission and be very cheap that way, because, again, they're under a meter in diameter. These are not large probes by any means. They're really small. And that's the goal of them, is to make them very compact. So let's say we are going with the main mission, which is to carry 6 of them all at the same time on a spacecraft bus with propellant inside. Now, next week, I'll actually go over into the orbital mechanics more and do a video showing the current stage of my script. Yes, I could use GMAT for it, or SDK. However, I don't have access to SDK, and going through the GMAT files, documentation, not worth it to me. I would rather do it all in Python. It is far better and easier for me to wrap my head around, and it's a big time saver. Trust me on that. Okay. So I've done a similar project in a class before, actually, where we needed to go to Phobos. And it had a similar-ish spacecraft mass. So I kind of piggybacked off of that. But let's go through our options anyway. So obviously the first is the venerable Falcon 9, especially Block 5. Super, super reliable, very cheap for launch vehicles, that is. They're touting 70 million. And of course, with all of these, there's delay costs and insurance costs. So ULA launches tend to have less, the cost for the insurance is less than SpaceX launch, at least to sources I was told. So of course here we have our capacity. So that's actually the ability for the launch vehicle to go into LEO. Now we get to Mars by doing a trans-Mars injection burn. And we're going to zoom in a little bit on here. So we've got the sun here, and we've got the Earth's orbit here, and we've got Mars orbit here. So let's say your starting point is right here at the Earth. And so you're going to do this translunar or trans-Mars injection burn. And it's going to put you into heliocentric orbit, which is orbit around the sun. It's just you've hit escape velocity or C3. And C3 is just the minimum amount of energy that you need to leave the realm of a body, pretty much. And you have 3 different maneuvers. So A, you have a Hohmann transfer, which is the least amount of delta V, but this requires for you to be circularized and in the same plane. And plane changes and circularization are just more burns. So that is path A. So you burn here, and then you glide, then you meet up with Mars. Pretty simple. B is a conjunction mission. Conjunction is when you are closest the Earth and Mars, and so this is generally the shortest time path. This is the second best for delta V. You can also do opposition. And opposition has some benefits. This is, of course, assuming no gravity assist via Venus, which can be possible. And with that, it could actually lower the delta V by quite a bit. So, as of this moment, subject to change with the design of everything, I do have proper CADs now, kind of, and I'll talk about those on a future date. But for now, I just want to talk about launch vehicle and do some other general updates. So, with the Falcon 9, it can bring about 18,000 kilograms. So mine's at about 7,500 wet. And that's not including the stage adapter and everything. That brings it up to, I believe, 8,800 kilograms. So we are obviously very much within that margin. And you can do an expended launch. Basically, it just means that everything isn't recoverable. And that means it's more expensive, but I believe it'll be more like 90 million, maybe 100 million for Falcon 9. I'm not quite sure. It's hard to find. And then you can also go to GTO, which is just geostationary. Means that when you're orbiting around, you are basically facing the same point on the Earth. It's your orbital velocity matches the rotation of the Earth. That's it. Obviously, you're in a much higher altitude, which requires more delta V to get there. So that brings down our mass requirements right there. And as you can see, like let's say we wanted to get our spacecraft to GTO, that means we would have to get a fully expended, and that's it. Or to do a Trans-Mars injection here, DMI, it's 4,000. Of course, I'm going to Mars, and I just told you that my mass is over 8,000. So how are we doing that? Well, we've got onboard propulsion. It's hydrazine. Biprop is more efficient. However, biprop generally means that it's going to be cryogenic. And cryogenic has boil off. And if you're going to be cruising for 300-ish days, then you're going to lose a lot of propellant. You're going to lose basically all of your propellant. Hydrazine is far more efficient for long term. So we will do a fully expended launch using the Falcon 9. And while it won't get us all the way in the second stage, it will get us quite a bit of the ways there. So with that, let's look at some other launch options. So kind of a nice big heavy launch vehicle by the Russians is the Proton M. I believe it's derived from the Proton something else. I don't remember the original version. That was extremely unreliable. Now it's been reined in with the Proton M. Proton M is very reliable. So as you can see, the capacity is roughly the same as the Falcon 9, a little bit less, and the cost is a little bit more. That's just simply how it is. And so due to even $5 million difference, and obviously I would be doing a fully expended launch, because again, you can see just an LEO, that's a huge difference right there. It just makes more sense to go with a higher cost vehicle, because we'll get way more out of it than we will in Proton. Okay, ULA. They have sent a lot of things to Mars. They sent Mars Science Lab. They sent Mars 2020 on a Vulcan Centaur. Well, let's see their cost per launch. It's $110 million. Now, based on our range, it could, for an expended Falcon 9, it could be like 90 to 100. So this is about $10 million more, which is quite a bit in a mission that's trying to be in the Discovery class missions and below. However, its payload size is quite significant. And if the cost is worth it to me, I can change it over to translunar injection. Translunar injection, wow, I'm just not reading. So that's a translunar injection, which is far easier than a trans-Mars injection. But ultimately, Vulcan is not better than Falcon 9. If you use the math, it can send less to Mars than a fully expended, I presume it's fully expended. SpaceX doesn't say on their website, probably because they don't have that many customers thinking about that, but still, I would say it's out because the decently higher cost, and it is just less viable in general. Well, let's look at the other Falcon-derived launch vehicle, Falcon Heavy. It can send a lot. Its base is basically just 3 first stages. And you can see that with the mass when fully expended. That is basically 3 times that of Falcon 9 Block 5. And the payload to Mars could easily bring our payload to Mars. In fact, my original design for it, I think it was around 2,200 kilograms, which all by itself would be quite a bit. But of course, when you add more mass to your orbital, I have my different stages and I call it the orbital. I need a better name. But that's just after the second stage and before the probes get released. That spacecraft bus is the orbiter stage. And, obviously when you put more mass into it, it lowers your delta V, and then you need more mass. But if you're able to use your launch vehicle to help boost you into that orbit, well, then you can bring the mass down and just do that iterative design of, okay, well, now I have X amount of excess. Let's say I want 5% extra fuel, which doesn't sound like a lot, but it kind of is, for the orbit stage, that is. So this is a very good, viable option. However, it's quite a bit. Now, of course, seeing this cost of reusable makes me think that the fully expended may be a lot cheaper than I think. And I'll put numbers right now. I'm giving myself time to put in the actual number if I can find it, to correct myself. So, New Glenn. Well, New Glenn is a launch vehicle that, as of this recording, has launched once, and it had a successful payload. It is pretty large. Cost per launch has been iffy because it just doesn't have the experience yet of the Falcon family. Just fine, that's fully expected. With one launch under your belt, you can't really price it out properly. You don't even know how it'll be recovered, and that'll load on your costs. So I see this, and I'm thinking it's more on the higher end, but that's right now. Maybe, in our launch window of 2028, it gets it down to that 68 million. Who knows? But as we can see, it can put a lot into low Earth orbit. To geostationary, it can also send quite a bit more than Falcon 9. So this is a viable option. It is. But at that current launch cost and the flight experience, it may not be worth it. And simply, you want your vehicle to be reliable? I'm going to trust it to a Falcon 9 over New Glenn. That's not because of any bias. It's just when you've had one launch, it says it right here. Sure, this is 100% success rate. But it's just far easier. Now, as I click onto this tab, I actually realized something. I love this. I love the Delta Heavy. It's an amazing launch vehicle. I did just remember that it's been retired. But we're going to compare it anyway because I think it's important to know the historical comparison, especially with Falcon Heavy. It's the same general layout. Look, we've got two first stages that are boosters, and this makes sense. And when you see cost per launch, you're going to see why ULA doesn't make them anymore. It's the amount of payloads that actually need this mass sent to orbit. They're not going to use 3 times the cost of a Falcon Heavy. Why would you? That is bad business. And so it makes sense that they cut it. Translunar injection, 8,000 kilograms. So it could send my payload all the way to Mars. However, I have onboard propellant. So it'd actually be far less than that if I used it all the way. And that's kind of the balance, right? Is what is better? More onboard propellant, or have the launch vehicle do it all the work for you? The launch vehicle is going to be far more tested and far more reliable than your one-off system. That's just a fact. However, it's going to cost a lot more. So you're going to have to accept that risk if you want to go down the cheaper route. And that's what I'm doing. Partially because it's more interesting. It's easier to calculate. Because, I'm not like making up numbers. You'll see with my orbital calculation, I have to take a lot of assumptions with the Falcon 9 second stage, which is okay. There's a lot of publicly known figures, and you can do a lot of derivation from that and kind of just assume a whatever factor of loss. And with that, I can still actually use the Falcon 9. So, obviously no Delta Heavy. Well, China has the Long March 5. It's a pretty reliable launch platform. Cost is high, but not terrible. But, maybe it offsets, our translunar injection, or transmars injection, sorry. No, it doesn't. So, talking about all these, let's look again at the Falcon 9. It's the cheapest, and it can send, 18,000 kilograms to LEO, non-expended. And an expended can send 2,200, or 22,000, sorry. And with that, my payload can easily use the Falcon second stage to just help me. So I'll use the leftover stage and then ignite my engine. Which again, I'll talk about more next week. I'm kind of sorry that this week isn't that much, but the payoff will be good. And I'll actually start publishing my code onto GitHub. There's 2 reasons for this. I want other people to kind of review and validate my code. And the other thing is, yesterday I may have written over my code by accident and lost a version that had gravity assists. So I'm currently actually rewriting that because it's useful. Kind of just to toggle switches, because again, I'm building my own. We're not relying on anything other than basic Python libraries and an Astro library or 2. So with that, thank you very much for watching. I know this is kind of just me looking at Wikipedia, but let me know if there's anything I should do, or you have any comments about the design or the videos or whatever, feel free to leave a comment. Thank you very much for watching. Have a good day. Bye-bye.